Let's talk about putting together some of the ideas that we've already seen. And actually today I'm going to mostly talk about some randomized algorithms. Remember when we talked about quicksort, I told you that randomized quicksort actually works really well in practice and the expected runtime is actually n log n. I made a promise that I will prove this to you and I'm going to do it today. And I'm also going to show you some relations between quicksort and binary search trees. And then if we have time, we're also going to see a data structure, which is a combination of a binary search tree and a heap. Okay, so let's start with randomized quicksort. So remember that the main idea in quicksort was that I want to sort an array of size n. I choose some element as the pivot, and then I compare this pivot with every other element. And I divide my array into two sets, the set of elements that are smaller than my pivot and the ones that are larger than my pivot. And then I sort each of them separately, recursively, and I don't have to do merge. That was the whole point of quicksort, that I don't have to do merge because I know the order of the two sets. So let's again imagine that this is my array. And let's say the indices are from 1 to n or whatever. And I'm going to just pick some pivot x. Or actually, let's call it p because it's a pivot. And then I'm going to go over all of my elements, and I'm going to find all the elements that are smaller than p, and I'm going to put them before p. And I'm going to find all the elements that are greater than p and put them after. And let's say if they're equal, I put them to the left. Okay. So this was our idea of quicksort, very simple. Now we talked about the different strategies for choosing the pivot. We've already seen a very nice strategy, this idea of always taking the best possible pivot, which is the median. And we saw an algorithm for finding the median in linear time, which would let us have a quicksort which wasn't randomized at all and gave us a runtime of n log n in the worst case. But now I want to talk about randomized quicksort, which basically says at any given step, just choose your pivot randomly. So choose each one of the elements as pivot with the same probability. So if I have n elements, I would choose each of them with probability 1 over n to be my pivot. Okay. Now, here's the thing. To analyze the runtime, I'm just going to analyze the number of comparisons that my algorithm makes. Because quicksort is a comparison-based sorting algorithm. And if I just know the number of comparisons, that's basically the same as my runtime, except for a constant factor. Okay. So what is the number of comparisons? We talked about this when we were talking about quicksort, that in the worst case, I'm going to be really unlucky. And every time that I'm picking a pivot, maybe I pick the smallest possible number as the pivot. And then I will have a recurrence that looks like this. T of n is I'm first doing n minus 1 comparisons with the pivot. And then I'm breaking my array into a left side, which is empty, and a right side, which has all the other elements. So I don't have to sort the empty one, but the right side will have T of n minus 1. And we saw that this is going to give me a runtime of O(n) squared. And actually, we saw that in the worst case, this is theta n squared as well. So the worst case is just n squared, which is not great. But let's say I want to look at the expected runtime. Okay. And this is what I defined last time as well. So when I'm saying expected runtime, it's really important to emphasize that I'm not saying the input is somehow randomly chosen. My input is always going to be the worst possible input that I can get. I'm always doing worst case analysis. I say expected runtime in the sense that I have randomization in my own algorithm, right? So the input is fixed, but I'm randomly choosing pivots every time. That's where the expectation comes from. Okay. So my expected runtime is basically something like this. I'm saying take the maximum over all instances that have a size of n. Actually, let me write it like this. Let's say I want to show my expected runtime again with t of n. I'm going to say this is the maximum over all possible inputs or instances that have a size of n of the expected runtime of my algorithm or expected number of comparisons over this instance. And this expectation is, of course, taken over the randomized choices that I'm making in choosing my pivots. So again, when I talk about expected runtime, I'm still doing worst case expected runtime. Worst case in terms of the inputs of size n that I'm taking. Okay. So let's do this. If I have an instance of size n, first of all, to just simplify my analysis, let's just assume that I just have the numbers from 1 to n, right? Let's say that this array, instead of just saying that I have n numbers or n items that I can compare, let's just say the numbers 1 to n are in this array in some order. Because I just want to count the number of comparisons that my sort is going to do. And this is not going to change the number of comparisons, right? So without loss of generality, I'm just going to say that my array just contains the numbers from 1 to n. Okay, so without loss of generality, I am sorting the numbers from 1 to n. But of course, they are not in this order. They're in some other order. Okay, so now what is T of n? The expected runtime, if I'm sorting the numbers from 1 to n, well, I can just do a casework, right? So I can say I will choose each one of my numbers as my pivot with the same probability 1 over n. So for every p from 1 to n, I have 1 over n probability of choosing this one as my pivot, right? And actually, let me just write I instead of p. I prefer I. For every I from 1 to n, I have 1 over n probability of choosing this particular I as my pivot. And if I do this, then I will have I minus 1 elements that are smaller, and I will have basically n minus I elements that are larger. So with probability 1 over n, I'm going to get t of I minus 1 for the left-hand side and t of n minus I for the right-hand side. Now I can put this 1 over n outside the sum. So I can write it like this. I can say 1 over n sum of t of I minus 1 plus t of n minus I, right? And of course, in any case, I'm also doing n minus 1 comparisons with the pivot. So all of this plus n minus 1. Now, this was the recurrence that we had last time, and I promised to you that I will prove that the answer to this is n log n. Now, you can try proving this with induction. It's not impossible, but it will be very painful. So I'm going to give you a simpler way of analyzing the number of comparisons here. So here's what I'm going to do. Let's say that I define a random variable, and let's say I call that random variable xi. So I say xi is going to be the number of comparisons involving I. Okay. So this is just number of comparisons involving I. Right. So how many other items have I compared with I? That's xi. Okay. Now, what can I say about Tn? I can say that Tn, which is my total number of comparisons, is just going to be the sum of xi's, but I'm counting every comparison twice. So if I'm comparing I and j, I'm counting it once in xi and once in xj, right? So I can say that Tn is just the sum of all the xi's, I from 1 to n, divided by 2, but I'm not going to do the divide by 2 because I want to do asymptotic analysis. I don't care about that. Okay, so instead I would just say that Tn is in the O of this sum. So I want to find this sum. Okay, here's what I can do. I can define more random variables. So let's say I define a random variable xij, and I basically make what's called an indicator random variable. So I say xij is 1 if I is compared with j. If at some point in my algorithm, I compare I and j, I say xij is 1. And I would say it's 0 otherwise. Okay. So xi was the number of comparisons involving I. Xij is basically whether I have compared I and j. So now I can very simply say that xi is going to be the sum over every j of xij. Right? Great. Now, if you remember from your 2711, is that it? Discrete math? 2711 or hopefully 2711H course, I can take the expected value and we have linearity of expectation. So if xi is the sum of xij's, its expected value is also the sum of expected values of xij's. So the expected value of xi is basically the expected value of sum over every j of xij, which is basically the sum over every j of the expected value of xij. Now, here's something. I just realized my life would be easier if I don't consider ij and ji separately. Okay, so let's do this. When I say xi, let's say number of comparisons involving I with some other number j that was greater than I. So I want to count everyone exactly once. Now here I can say that my T of n is just the sum, right? Because now I'm counting every comparison once. Basically, I'm saying whenever you're comparing I and j, just count it for I, don't count it for j, right? And I say xij is 1 if I is compared with j, 0 otherwise, and then this one would be the sum over all j's that are greater than I of xij. So this doesn't change anything, it's just a factor of 2, makes my life easier. Okay. So here's the thing. If I can find the expected value of xij, then I can sum them up. I can find the expected value of xi. And if I do that, then I can sum those things up and I can find the expected value of Tn, which is the expected number of calculation, the expected number of comparisons that I'm doing. So basically Tn was, the expectation of the sum of x's. Okay. So here's the thing. I have a variable, xij, it's either 1 or 0. So the expected value of this variable is just the probability that it would be 1. Right? Just use the definition of expectation. So it's 1 times the probability of being 1 plus 0 times the probability of being 0. But that 0 cancels out. Okay. So basically, I want to know the probability that xij is 1. But that's just the probability that I would ever compare item I with item j. right? That's what I want to find. So the expected value of xij is the probability that sometime during my quicksort, I compare I with j. Okay. So if I find this probability, hopefully I can analyze all of my quicksort. But now I want you to think about how quicksort works again. So let's say I have a bunch of numbers. Let's say I have all the numbers from 1 to 8. Okay, and they're not sorted initially, so they're in some order. Now I'm going to choose some pivots. And let's say that the pivot that I chose was 6. So my n is 8. I chose 6 as my pivot. Now what's going to happen? I'm going to go over all of my elements and compare them with 6. And all the elements that are smaller than 6 are going to go to the left side, basically. And all the elements that are larger than 6 are going to go to the right side. Okay? So using 6, I'm basically going to divide my elements into 2 parts. These are all the elements smaller than 6, 1, 2 to 5. And on this side, I will have all the elements that are larger than 6. In this case, just 7 and 8. Right? But then I'm recursively sorting each one of these 2 sets. So on this side, I'm going to, again, randomly choose another pivot. And then I'm going to divide my items into those that are smaller than the pivot, who go to the left, and those that are larger than the pivot, who will go to the right. So for example, if the pivot that I choose for here is, let's say 4, I will have 1, 2, and 3 to the left. I will have 5 to the right. And again, between 1, 2, and 3, I'm going to choose some pivot randomly, let's say 2. And then I will have 1 to the left, 3 to the right. And I do the same thing here, some pivot randomly, say 8. And this is a binary search. Right? Because basically, I mean, that's the same rule that we had in a binary search tree. You take the root, all the elements that are smaller than the root go to the left. All the elements that are bigger than the root go to the right. So this is the connection between binary search trees and quicksort. In some sense, they're doing the same thing. Okay, so for every instance of my quicksort, I can create a binary search tree. Well, not for every instance. For every run of my quicksort, I can create a binary search tree. Now, here's the thing. When are 2 items compared with each other in my quicksort? They're compared with each other if one of them is an ancestor of the other one in this binary search tree, right? So when I take 6 as my pivot, I compare everything with 6. So everything is compared with 6. But then on this side, when I took 4 as my next random pivot, every remaining thing, 1, 2, 3, and 5 were compared with 4. Because I had to figure out which ones go to the left and which ones go to the right. Right? So basically, when I say what is the probability that I would compare I with j in my quicksort, that's the same as the probability that in this random binary search tree, I is an ancestor of j, or j is an ancestor of I, one of the 2 cases. Okay. Now, so here's a question. Let's say I give you a fixed I and a fixed j. When would I become an ancestor of j? So for example, let's say I say I is 4 and j is 7, right? In this particular tree, 4 is not an ancestor of 7, and 7 is also not an ancestor of 4. What should happen in my quicksort to make one of these numbers an ancestor of the other one? So of course, okay, let's just focus on this. Suppose that I want 4 to be an ancestor of 7. So of course, 4 has to be chosen as a pivot before 7 is chosen, right? That's of course the case because I'm only comparing with pivots. All these ancestors are pivots. But if I look at all the numbers in between, so let's say I look at 4, 5, 6, and 7. If I choose any of these numbers in between as pivot before 4 or 7, then they will go in 2 different directions, right? So for example, here I chose 6 as my first pivot and 4 went to the left and 7 went to the right. So that would ensure that I will never compare 4 and 7. So the only way that I would compare 4 and 7 is if I choose them as a pivot before 5 and 6, right? Because if I choose any of the numbers between 4 and 7 as pivot before I choose either 4 or 7, then they will just go into 2 different directions and I will never compare them. Now, I can say this for any value of I and j, right? So if I have I can look at all the numbers I plus 1, I plus 2, all the way to, let's say, j minus 1, j. And the only case where I and j will be compared with each other, the only case where I would be an ancestor of j or j an ancestor of I, is that they're chosen as a pivot before everything that comes in between. Okay. But here's the thing, I'm choosing my pivots uniformly at random. So every time that I'm choosing a pivot, all of these numbers have the same chance. They have the same probability of being chosen as my pivot, right? So the probability that the first pivot that is chosen between I and j is either I or j is at most 2 because I have 2 desired choices, I and j, divided by the number of these numbers, which is j minus I plus 1. Okay. So that's the probability that I would compare item I with item j. And the probability that I compare item I with item j was the expected value of xij. So it's 2 over j minus I plus 1. Okay. Now I can plug this back into all of these sums. So what was my T of n, the expected total number of comparisons? It was just the expected value of the sum over every I from 1 to n of the sum over every j, let's say from I plus 1 to n of xij, right? But again, we can take the sums out because of linearity of expectation. So this is just the sum over every I, the sum over every j from I plus 1 to n of 2 over j minus I plus 1. Okay. Now I have a nice sum. I hope that you agree that this is nice. And I want to prove that this is n log n. Now, here's the thing. First of all, let's take this 2 out. Let's put the 2 here. And let's just write 1 over this. Now look at this sum. What is this sum? So this is 1 over 1 plus 1 over 2 plus 1 over 3, so on. And it stops at some point. But I can approximate it, and I can say this has at most n terms. So this sum is going to be at most, okay, I'm going to put everything that I had before, I from 1 to n. But for this sum, I'm just going to say sum of k from 1 to n of 1 over k. Right? This is an over approximation. Okay. But what is this blue sum? The sum of k from 1 to n of 1 over k. Yeah, this is harmonic, and basically it's log n, right? It's in theta of log n. Because you can, well, if you need the proof, you can just think of the integral. So the integral of 1 over x dx is basically the log function, the natural log. And this is like a discrete version of the integral. You can just think of the rectangles that you have in integrals. So anyway, this part, the blue part, is basically theta log n, right? But here's the thing. On the other hand, I have a 2 here, and I have this sum of I from 1 to n, which is just summing up the same thing over and over again. So all I have is 2n times the sum of k from 1 to n of 1 over k. But we saw that this sum is log n, so this is in O of n log n. Because this part is log n, I don't care about the 2, I'm using O notation. So I do n log n comparisons in my quicksort. Again, this is the expected number of comparisons, and the expectation is taken over the randomness that comes out of the algorithm, the randomness that we had in choosing our pivot. Okay, and we also saw a really nice connection to binary search trees. Great, now based on this, or maybe, well, not necessarily directly based on this, but similar to this, I want to now define another data structure. And this data structure is called a treap. So it's a treap because it's a mixture of a tree and a heap. Okay, that's what they call it. And the idea here is, again, kind of simple. So until this point, we were talking about sorting some items, and we were thinking of them as numbers. So I had a bunch of numbers. Every element was one number. Now I want to say, imagine that every element is 2 numbers. Okay, so I have n elements. And let's call them E1, E2 to En. But every element has 2 numbers. So every EI has 2 parts. I'm going to call them KI and PI. So it has a key and a priority. Those are the words that we're going to use. So this KI is a key, and this PI is a priority. Okay. Now, here's what I want to do. I want to create a binary tree on my elements, and I want to make sure that it's a binary search tree when I only look at the keys and ignore the priorities. And at the same time, I want it to be a max heap when I only look at the priorities and ignore the keys. Okay, this is what I call a treap. So if I just want to write the definition here, a treap is a binary tree over the EIs, over the elements. Which satisfies the binary search tree properties if I only look at the keys, and the max heap properties if I only look at the priorities. Okay. Now, of course, again, unlike a normal heap, this is not going to be a complete or almost complete tree. It's just going to be a binary tree of any shape, but it has to satisfy the binary search tree properties on the keys. So every node should have a key that is bigger than everything in its left subtree and smaller than the keys of everything in its right subtree. But if I only look at the priorities, it should be satisfying the max heap property, which means that the priority of every node should be larger than the priority of all of its descendants. Okay. And also to make my life easier, I'm going to assume that all of the keys and priorities are distinct. So I don't have two elements with the same key and I don't have two elements with the same priority. But I mean, even if they're not distinct, all of the algorithms that I give you work, they just will have some corner cases. It would be harder to implement. Okay, so all keys and priorities are distinct. And of course, as usual, I'm just going to assume that the keys and priorities here are integers, they're numbers. But in practice, all I need is to be able to compare them. So as long as your keys are comparable with each other, you can say which key is larger and smaller. And as long as your priorities are comparable, you're fine. Okay, let's do an example. Let's say I give you a bunch of these elements. And again, remember, every element has a key and a priority. So I'm not a good random number generator. Let's say 10, 0, 2, 5, 1, minus 2, whatever, 0, 10, 6, 7. Let's say these are my elements. And in every element, I write the key first, and then I write the priority. Okay. So let's say I want to create a tree on these elements. So can you do it? Can you create a tree on these elements? So my first question is, what should be at the root of my tree? So I can just look at my priorities and I can find the element with the largest priority, which is this one. 10 is the largest priority. And because I should have the heap property on priorities, the largest priority should always be at the root. So I know that this element has to be at the root because it has the largest priority. So when I'm creating my tree, I have to put 0, 10 as my root. Okay. But as soon as I do this, I know which elements should go to the left and which elements should go to the right. Right? Because it has to be, okay, not a good example. Let me put like, yeah, let me put -1, 8 here as well. Okay. So I know that 0, 10 is my root, and I know this based on the priority because it's the node that had the largest priority. Now, based on the keys, I should have a binary search tree. So all the nodes that have a smaller key, all the nodes that have a key less than 0 should go to the left. All the nodes that have a key larger than 0 should go to the right. So in this case, because my example wasn't great, I have only one node that has priority less than 0, and that's -1, 8. So this one goes to the left. And all the other nodes should go to the right. Okay. But again, if I just consider the nodes that are going to be in the right subtree of the root, which node should be the highest? Which node should be the root of that subtree? The one that has the highest priority. So who has the highest priority here? This one, 6, 7. Okay. So I put 6, 7 here. And again, I have to look at the keys. So this has a key of 6. Anything that has a key smaller than 6 will go to the left side. Anything that has a key larger than 6 will go to the right side. And in this case, I have only one element that has a key larger than 6, and that's 10, 0. So that one goes to the right side. And everything else, these two elements have to go to the left side. But again, which one is going to appear higher? Which one is going to appear as the root? The one that has the higher priority. So this one, 2, 5. So I will have 2, 5 here. And then finally, 1 minus 2 should go to the left of 2, 5, because if you compare the keys, 1 is less than 2. So I will have 1, and -2. Okay, so this is my tree. Now, if you look at the keys, if you look at the first component, it's a binary search tree. I have 0 here, -1 here, and all the numbers here are greater than 0. Again, I have 6 here, 2 is smaller than 6, 10 is larger than 6, and so on. So it's a binary search tree if you only look at the first component, if you only look at the keys. But if you only look at the second component, if you ignore the keys and only look at the priorities, you see that this is a max heap, because 10 is larger than 8, 7, 5, 0, and -2. And generally, every node is larger than all of its descendants. Okay. So now, of course, we want to do all the operations that we were doing on our previous things, on our previous data structures here as well. So specifically, I want to be able to insert into this data structure. I want to be able to remove from it. But before doing all of that, I just want to remark that for any given set of elements, as long as you have distinct priorities and you have distinct keys, you have exactly one treap. So this data structure is unique, right? Because if you just trace the algorithm that I had for creating this, you see that I didn't have a choice at any point. At the beginning, I had a unique choice for the root. I have to put the element with the highest priority as my root. There is no other choice. And as soon as I do that, the division between left and right is unique. All the elements that have a smaller key should go left. All the elements that have a larger key should go right. Right? And then I can just continue the same argument. I can say on the left side, I have a unique root. On the right side, I also have a unique root, and so on. So I have a unique treap for any given set of elements, as long as I have distinct keys and I have distinct priorities. So no two elements have the same keys and no two elements have the same priorities. That's great. And also, well, how much time does it take to create this tree? If I give you just all the elements and I ask you to create the tree. I want you to recognize the relationship with quicksort here. So basically, what's happening here is that I first have to find my root. And to find my root, I just go over all of the elements and I find the one that has maximum priority. Now I have to compare the key of the root with every other key, because I have to figure out which elements go to the left and which elements go to the right. Right? So the key of the root is like the pivot in my quicksort. I'm comparing it with all the other keys. So actually, my worst case here is very similar to the worst case of quicksort. And my worst case is when my tree is just a path. So I had to compare every pair of keys together, and that's like n squared comparisons, O(n) squared comparisons. Okay. So it seems like creating this tree is not that great of an idea, but we will talk about it and you will see how we will actually use this. For now, I want to talk about inserting elements and removing elements from my tree. But before doing that, I want to talk about a different operation, which will be used in both insertion and deletion. And that's changing the priority. Okay. So suppose that I give you one of these elements. For example, I give you this 10, 0, and I say I want to change the priority. I want to change 0 to something else. Now, you can think of this as two different operations, increasing the priority or decreasing the priority. So let's first do increase priority. So here's how this works. So increase priority, it takes a key and it takes the new priority. Okay. And it says basically increase the priority of this key from whatever it was before to P prime. So for example, I can have increase priority 10, let's say 12. So this means that I have to take 10. Its priority was previously less than 12. I have to increase it to 12. Okay. Now, let's just copy this thing. Let me see. Let's copy it and let's try to do this increase priority. Okay, first of all, in order to increase the priority associated with a particular key, I have to first find the node in the tree, right? But finding is easy because remember, this is a binary search tree. So I can just find 10 because I can do search in the same way that I did search on binary search trees. But very importantly, I can do search on my keys. I cannot do search on my priorities because by priorities, it's a heap. And in a heap, we didn't have searching, right? But that's fine because I'm giving you a key and I'm saying change its priority to something new. So the first thing I do is that I search for this key. So I'm searching for key 10. I start here. I see that 10 is greater than 0. I go to the right. 10 is greater than 6. I go to the right. I find it. Okay. So now I have found this node. I see that it has key 10 and priority 0. But I want to, let's say, increase the priority to 12. So let's say I change this priority from 0 to 12. Okay. What happens now? Well, first of all, I didn't change any of the keys. So my binary search tree property is there. It's not violated. But the problem is that because I increased this priority, maybe my priorities are no longer satisfying the max heap property. Okay. So, and that's exactly what's happening here because this 12 is larger than this 7. So I'm violating the heap property. What should I do? Well, in a heap, I would just do bubble up, right? But here I can't just do bubble up because if I just do bubble up, if I just swap these two, then I would violate the binary search tree properties. So I somehow want to take this element and I want to move it up, but I want to move it up while preserving the BST property. And this is where the rotations from last session come in. And I actually kept that particular slide, if we can call these slides or board. Look, this is what we were doing. We had this A and B. I wanted to move B up the tree. And I would just do a rotation, right? And this would bring B above A. And this is exactly what I want here. If I go back here, I want this node, 10, 12, to be above this node, 6, 7. Right? But I want to also satisfy the binary search tree properties. So I'm just going to do rotation. I'm going to do this rotation. I think it's like R1 of 6, 7. Okay. So let me just copy this tree and show you how it would look like after the rotation. So I do R1 of 6, 7. Hopefully I wrote the rotation correctly. Maybe it's R2. No, it's R1. Okay. So if I do this rotation, this part of the tree doesn't change. So I will have 0, 10 as my roots, and its left child is minus 1, 8, because I didn't touch that part at all. But I'm doing this rotation here, so 10, 12 comes up. And then its left child would be 6, 7. Right? And then the left child of 6, 7 would be 2, 5. And the left child of that would be 1, minus 2. Okay. Now you're already seeing what kind of horrible things can happen. I'm again having a really awful height here, but this is not done yet, right? Because remember when I was doing bubble up in my heap, I had to keep doing bubble up. And here it's the same. So I solved the problem between 10, 12 and 6, 7. 10, 12 is now above 6, 7. But now 12 is even larger than 10. Right? So I have to move it up one more time. So I have to do another rotation because the only way I can move items up now is by rotations. because I know that rotations preserve the binary search tree property. So I do another R1, this time on 0, 10. And basically doing this, 10, 12 becomes the root. 0, 10 becomes the left child, right? And then I have 6, 7, which is the right child of 0, 10. And I have -1, 8, which is the left child. And then I have the rest of it. So 2, 5, and 1, -2. Okay. And now I finally have a valid tree. So now if I look at the things here, if I look at the keys, it's a binary search tree. So 10, every other key is smaller than 10, and so everything is on the left side. And you can also look at this, like I have 0, -1 is smaller than 0, 6, 2, and 1 are larger than 0. And if you look at the priorities, you can see that it's a max heap. Unless I've had a bug, but no, this is a max heap. Okay. So that's how you would increase a priority. You basically first search based on the key, find the node, increase the priority, and then you have to bubble it up, but you cannot just do bubble up, you can only do rotations because you have to satisfy BST properties. So you keep doing rotations until you solve all of your problems. Until you make sure that basically the heap property is satisfied everywhere. What is the runtime here? It's again OH, where H is the height of the tree, right? Because I take this item, I have to move it up. Every time that I'm moving it up by 1 level, I'm doing 1 rotation. But in the last session, we saw that rotations take constant time. So I'm doing at most H rotations. So this is OH. Or to be more specific, it actually depends on where your node is. So if my node was like one of the children of the root, it would take O1. Right. So my runtime is basically linear in the level of the node that I'm moving up. So how many times can I move it up? But yeah, this is basically OH. And you see that history rhymes, and we have this problem that, again, we're spending OH, but our height is large. So this is not that great. But let's now talk about the opposite. Let's say I want to decrease priority. So I'm going to copy this again. And let's say now I want to do decrease priority. And again, just as before, my decrease priority is going to give you a key K, and it's going to give you a new priority P prime. But now this priority is smaller than whatever priority it used to have. Okay. So for example, maybe I want to decrease the priority of, in this case, let's say 6. I want to decrease it to, well, it was 7 before. Let's say I want to decrease it to 2. Okay. So just as before, I have to search for my key. I have to find 6, but it's a binary search tree. So I start at the top. I see that 6 is greater than 0. So I go right. I found it. Now the priority was 7. I'm changing that 7 to 2. Again, the situation is very similar to before. By changing the priority, I'm not going to violate any of the binary search tree properties. The only thing that I'm violating are the heap properties. And the problem is that, well, this 2 is now smaller than 5. So I have to do bubble down in my heap in some sense. But again, just as before, I can't just simply do bubble down. I have to rotate down. So I have to do a rotation to bring this 6, 2 down. But which elements should replace 6, 2? Well, the one that has the larger priority, right? So I have priority 5 here, but priority 0 here. So this one should come up. So if I copy this, this is what's going to happen. I want to do basically this kind of rotation. So this is R2 of 6, 7, or R2 of 6, 2. Right? So again, I didn't touch 0, 10, and minus 1, 8. So they remain where they were. Now 2, 5 takes the place of 6, 2. So I will have 2, 5 here. Now I'm doing this rotation. So 6, 2 becomes the right child of 2, 5. And then 10, 0 is the right child of 6, 2. And the left child of 2, 5 is minus 1, 2. Sorry, 1 minus 2. Okay. But just like before, we have the same situation. When you were doing bubble down in your heap, you had to keep doing it until all of the heap properties are satisfied. But in this case, I was lucky, and this priority 2 here is greater than 0, so I don't have to continue it. Okay. But of course, again, in the worst case, when I'm doing this, I might have to keep doing it until my node becomes a leaf. So my runtime here is also OH. Because I'm finding this node. I mean, even finding the node takes OH, right? But then when I find it, I have to move it down. But every rotation moves it down by only 1 level. I might have to move it down H levels. And every rotation also takes constant time, so it's OH over. So now we are in this nice situation where we can increase the priorities and we can also decrease the priorities. So how would you insert now? So let me copy this again. And let's just talk about insertion. Ooh, I can change the whole color. That's nice. Okay. So let's say I want to insert. And when I'm inserting, of course, now I'm going to give you 2 things. I'm going to give you a key and a priority. So I want to insert KP. Okay. For example, let's say that I want to insert 7 and whatever, 100. Or, well, 100 is too much. Let's say 7, 8. So 7 is my key, 8 is my priority. Now, here's the thing. I know the elements that are already in there, and I know the new elements that I'm inserting. And I know that for any given set of elements, there is only 1 treap. So there is exactly 1 correct answer here. Whatever algorithm you have, it has to create the same treap as any other correct algorithm. Okay. And remember, I can change my priorities, right? Because I can change my priorities, I can basically say I ignore the priority and I insert only based on the key. Or another way of looking at this is that I say, suppose my priority is minus infinity, or it's a very small number. It's smaller than all the other priorities. And I'm just going to insert with this assumption. Okay. So let's say I want to insert 7, 8. I just look at my key 7 and I insert based on the key. So I go 7 is greater than 0, I have to go right. 7 is greater than 6, I have to go right. 7 is smaller than 10, I have to go left. So I'm putting it here. But of course, with priority minus infinity. Okay. And putting a priority of -infinity is fine, because when I'm inserting in a binary search tree, I'm always inserting at a leaf. So if my priority is -infinity at a leaf, I'm happy. There is no problem with that. It's going to be smaller than all the other priorities anyway. But now I know how to change priority. Specifically, I know how to increase my priority. So now I will increase this priority from -infinity to 8. Which is basically the same thing as saying I do these rotations to bubble it up. Okay. So I did this. Now I'm going to, again, just copy this. After I inserted it as if I didn't have a heap and I only had a binary search tree, I'm going to increase this priority now to 8. Okay. Now this priority is bigger than this priority, so I have to do a rotation. So here I will have 7, 8, and then I will have 10, 0 as the right child, not the left child. Right? And then the rest of the tree is the same as it was before. So 6, 7, 2, 5, 1, -2. 0, 10, and -1, 8. Okay, so that's my first rotation. But now this 7, 8, this 8 is also more than this 7. So I have to do another rotation to bring this 7, 8 up. So I'm going to do the next rotation. Now I will have 7, 8. And 6, 7 becomes the left child. And remember when I was doing the rotations, I would just look at this. So 2, 5, so on, and 10, 0 here. So I would have 2, 5. I'm just adding them in the same order as before. 1, -2. And on this side, I had 10, 0, and I will just have 10, 0 here too. And again, the rest of my tree is exactly as before. So I have 0, 10, and I have -1, 8 here. And at this point, if I now compare this priority 8 with the priority of the parent, I have a smaller priority. So I have the heap property as well on my priorities. So at this point, I'm fine. Okay. So how much time does insert take? Again, it's OH, right? Because I'm just doing the insertion based on the key, and that's taking OH in a binary search tree. And then I'm just doing one change of priority, which we saw also takes OH. So this is also OH. So if you look at all of the things that I did with Treaps in this session, it seems like it was completely pointless, because all of our runtimes are basically the same as the runtimes that we had on binary search trees, right? So it seems like I'm just keeping this extra property of heap, and it's not really giving me anything. It's not even giving me a balanced tree. At least with the AVL property, I've got a balanced tree. I could say my height is log n. But here I can't even do that, right? Now, how would it actually help? The way it actually helps is that I can use it to create a randomized binary search tree. So let's say I want to create a binary search tree on a bunch of keys. So no one has given me priorities. They have just given me n different keys, and I want to create a binary search tree over them. I just add random priorities for all the keys, and then I create a tree. Okay. It seems very strange, but that's what I'm going to do. So randomized binary search tree. This is basically the situation I'm in. I have some input, and these are my keys. So key 1, key 2, all the way to key n. And what I'm going to do is that I'm going to generate the priorities myself. And I'm going to generate them randomly. Okay, so one way of doing this is if you know how many elements you have, you just take the numbers from 1 to n and you give a random permutation to them. Because we don't actually care about our numbers, we just care about the order between the numbers, right? Another way of doing it is that whenever you want to insert an element, you just generate a random priority for it before insertion. And the priority that you generate is, let's say, a random number between 0 and 1. Okay. I don't care how you generate your random priorities as long as you're making sure that they're uniform. So for any 2 keys, the corresponding priorities should be randomly ordered in the sense that the probability that the priority of K1 is bigger than the priority of K2 should be exactly 50%. Okay. So I just say generate random priorities. I'm going to call them P1, P2 to Pn. And you can imagine that all of these are just real numbers between 0 and 1. Okay. And then I say create a treap based on this. So create a treap based on K1, P1, K2, P2, so on to Kn. Okay. Now, again, this is just creating a random binary search tree or a random tree. But generally, if I want to delete an element, I just delete it in the same way that I delete an element from a treap, right? Oh, I didn't talk about deletion, did I? I forgot that. How do you delete something? Let's actually talk about that. Sorry, I forgot that. If I have a treap, how would you remove an element from your treap? Yeah, exactly. So we saw in binary search trees that if you have a leaf, if you have an element that doesn't have any children, you can just remove it and that's it. So here you can do the same thing. Just decrease its priority to -infinity, it will go down. And it goes down, becomes a leaf, you remove the leaf. Okay, so sorry for forgetting that. So I want to do remove K. And by the way, when I'm doing remove, I'm not giving you the priority because you don't need it anyway. You just need the key to find the node. And when you find it, you can remove it. I can also give you the priority, but what's the point? So remove K is going to be very simple. So we say find K using the binary search tree search. And then just do decrease key of K to -infinity. This would bring it all the way down to a leaf. And then we say remove the leaf. Remove the leaf that has K as the key and -infinity as the priority. Okay, so again, removing is also OH because it's basically BST search and then it's decrease key. We've seen all of these are OH. And of course, removing a leaf is just constant time. You're just removing one pointer. Okay. So in my randomized binary search tree, where I have random priorities, I want to also have insertion and deletion. So maybe instead of having all the keys in the inputs, I'm just starting with an empty binary search tree, and I just have insert and delete and so on. So how does this work? My insertion, so if I'm inserting K, it's going to be very simple. I just say choose a random priority . I'm going to say this is P. And let's say I take it from the uniform distribution on 0 and 1. So I'm taking a uniform real number from all the numbers between 0 and 1. And then I say just to insert pk in the treap. Very simple. And then removing is just the removing in the treap, because removing just gives you a key. And we saw that in the treap, I only need the key. I don't even need to know what the priority is. I can remove it. Okay. So remove k is super simple. I just say, basically call the treaps remove function. So treap.remove k. Okay, great. Now, if you look at this randomized binary search tree, which is basically a treap, my randomized binary search tree is a binary search tree based on the keys. So I can do all the binary search tree operations. I can do min, max, search, next element, previous element, sort, whatever. Everything that I did with binary search trees, I can do here as well, right? Now, the question is, what is the height of this tree? Because we saw that in binary search trees, it takes OH to do all the operations. And also in the treap, it took OH to do all the operations. So what is the height? Now, again, I can do a worst case analysis. And I can say in the worst case, my height is going to be n-1. Because imagine that I'm inserting these numbers. And every time I'm just generating these priorities. Oh, sorry, this should be insert KP. Let's say, imagine that I'm generating these priorities P, and I'm always generating them in an increasing manner. So every time that I'm inserting a new item, it's becoming the root of my treap, and it's increasing the height of my treap by 1, right? So my worst case here is that my treap is going to have a height of basically omega n, and then if I do these insertions and removes and so on, all of my operations are going to take linear time. If I do n operations, it would take n squared time. So if I want to use this for sorting, the worst case of my sorts runtime would also be n squared, because I'm doing n insertions. In the worst case, that's taking n squared. And then I'm just calling the sort function of the binary search tree. That's linear time, but who cares? At this point, I've already spent n squared. But just like the case of the quicksort, we want to talk about the expected runtime, right? And just like before, when I say expected runtime, I'm still doing worst case analysis. I'm still taking the worst possible input, but I'm saying the expectation is taken over the random choices of the algorithm. So what is my expected runtime? Or another question to ask is, what is my expected height? Because if I know the expected height, that's basically the expected runtime of every operation. And I just multiply it by the number of operations I have, and that's my total expected runtime. So this is the question. What is the expected height of the tree? Now, it turns out this is a hard question to answer. It's easier to ask something more specific. Remember when I was doing increased priority here, I said that the expected runtime of increased priority, well, of course, well, sorry, I didn't have expectation. I said that the runtime of increased priority is OH, but I said to be more specific, the runtime is going to be O number of ancestors of the current node, because I had this node and I was moving it up. So the question is, what is the expected number of ancestors of a particular node? Okay, so this is what I want to calculate. So instead of asking what is the expected height of the treap, I ask for a particular node. So let's say I pick one node, and you can take any arbitrary node. For a node let's say, or element KP in the treap, what is the expected number of ancestors? The expected number of ancestors of KP. Okay. So again, to make our life easier, I'm going to assume that my keys are the numbers from 1 to n. Okay, but not in that order. It's in some order. I have the numbers from 1 to n in some order because I only care about ordering here, just like the case of quicksort. So I'm going to ask for some particular node. So let's say my key is I. What is the number of ancestors of the node that has I here and some priority, some random priority, right? So how many ancestors can this node have? So I say xi is the number of ancestors of the node with key I. Okay. So I can do the same thing that I did for quicksort. I can define another variable. I can call this xij. And I say this is 1 if the node that has key j is an ancestor of the node that has key I. Okay. So I say this is 1 if the node that has j and some priority is an ancestor of the node that has key I and some priority. Again, the priorities are random. I don't want to write them. And it's 0 otherwise. Now, what do I want to find? I want to find the expected value of xi, which is the number of ancestors of I. But again, xi is just the sum of all xij's. So I can say that the expected value of xi is just the sum over all j. Of course, j should not be equal to I, of the expected value of xij. But expected value of xij is the probability that j is an ancestor of I. Okay. So if I'm creating this randomized binary search tree, if I'm giving random priorities to all the nodes, I'm asking you, what is the probability that j just happens to be an ancestor of I? This is the exact same question that we asked for quicksort. Okay, so here's what's going to happen. I have these completely random priorities, and I know that the node that has the maximum priority is going to be my root, right? So you can think of the root as the pivot in quicksort. All the nodes that have a smaller key will go to the left. All the nodes that have a larger key will go to the right. But how was the root selected? The root itself was selected randomly, right? Because I just gave random priorities to all the nodes. And then I said the node with the maximum priority becomes the root. So I'm choosing each one of my nodes as the root with the same probability 1 over n. And this is exactly like what I was doing in quicksort. I was just choosing one of the nodes as a pivot with probability 1 over n. So the analysis that I'm going to do here is exactly the same as quicksort. So again, I'm going to say, I want to see what is the probability. So this is the sum of j not equal to I, the probability that j is an ancestor of I. Okay. Now, again, I'm going to say, look at all the numbers from I to j. And remember, I'm just assuming my numbers are from 1 to n. So look at all the numbers I plus 1, I plus 2, all the way to j. So j minus 1, j. I have given some priority to each one of these keys. Okay, so maybe I have pi plus 1, pi plus 2, so on, pj minus 1, pj. Now, here's the thing. Every time I'm taking the item that has the maximum priority and putting it as the root and using it to divide my other items based on the keys, not based on the priorities. So if the item that I choose, which has maximum priority, is more than j, all of these items from I to j are going to go to the left side. In the same way, if the item that I choose as my root is less than I, all of the items from I to j are going to the right side. Again, remember, these are keys. These are priorities. Okay? So the only case where I and j will go to two different sides is if the root that I choose is somewhere between I plus 1 to j minus 1. If I choose any of these nodes as a root, I will go to the left, j will go to the right. Okay, when does j become an ancestor of I? If j is chosen before all of these. So the only case where j becomes an ancestor of I is if pj is bigger than all of these other priorities. Because in that case, j will be chosen as the root before all of these other ones, and then they will all go to the left side, and j will be above I. Okay? Of course, this was for the case where I is smaller than j. You can also do the case where j is smaller than I. It's the same thing. It's just the mirror image of this. So what is this probability? Again, the probability is just 1 instead of 2, because now I want j to be an ancestor of I, over the number of these elements, which is j minus I plus 1. Okay? So that's the probability that item j, the item with key j, ends up being an ancestor of the item with key I. Now, to be more specific, this should be the absolute value of j minus I, because maybe j is smaller than I, then you just take absolute value. Okay, going back here. I want to see what is the number of ancestors of xi, and I saw that this is just the sum of every j that is not equal to I, of the probability that j is an ancestor of I. So this is just the sum over every j that is not equal to I, 1 over the absolute value of j minus I plus 1. Okay. Now just calculate this. This is log n, right? So you can divide this in two parts. You can say this is the sum of all the j's from 1 to I minus 1 of 1 over I minus j plus 1, plus the sum of all the j's from I plus 1 to n of 1 over j minus I plus 1. So I'm basically doing a casework because I had absolute value of j minus I. I'm saying in these cases, it would be I minus j. In these cases, it would be j minus I. Now, in any case, if you look at each one of these sums, it's less than 1 over 1 plus 1 over 2 all the way to 1 over n, right? So these sums, each one of them is less than that. So all of them together are smaller than k from 1 to n, 1 over k, this sum times 2. But again, we saw that this sum is log n, and I don't care about the constant 2. So this is in O of log n. Right? So this means that for any given node in this tree, in this Treap, or in this randomized binary search tree, the expected number of ancestors is in O of log n. But the expected number of ancestors was my runtime. So I'm doing every insertion in O log n time in expectation. My worst case is still O n squared. Sorry, O n for every insertion. but my expected runtime is log n. So if I use it for sorting, my expected runtime for sorting would also be O(n) log n, right? Because I'm just doing n insertions and then I'm doing the sort function. But again, my worst case would be n squared. So I'm getting runtimes that are very similar to quicksort. And one final note, in practice, these kinds of sorts work better than the non-randomized kinds of sorts. So quicksort is generally much faster than merge sort in reality, like because of the small constant factors. And this is actually, if you implement a Treap and if you implement a randomized binary search tree based on a Treap, it would work better than an AVL tree. And I mean, it makes sense because it's simpler, right? We don't have those double rotations that we had in the AVL. But again, in theory, AVL is giving you O log n per operation in the worst case. This is giving you O log n per operation in expectation.